Today we are going to see that how we represent the decimal numbers in the binary, and actually we have to see that how exactly these numbers are present in the binary. In the last video I show you that how the negative numbers are represented in the 2's complement, and now we are going to see exactly that when you have any number, suppose I have some number like 16.75, okay, something like that. Okay, I am taking this value 16.7556, suppose. So we are going to see that when this number is going to store in the memory, then what is the bit representation of this number. So you can write here any number of bits, and we have to check that how this number is actually converted to the bit. So if I am trying to write this number into the by default in C language it take the float value, take the 4 bytes. So we are going to represent if value is very big, like in Python very big or very small, then it adjusts the memory accordingly, but in C language 4 bytes are assigned. So we are going to represent the number into the 32 bit. In 32 bit we say that it's single precision. That precision is something like if you write this number, suppose I am taking number 4.56, something like that. So up to how much decimal places your value is correct. So in single precision, that means if you are taking less number of digits, then you can represent up to 6 decimal places, 3, 4, 5, 6. Up to 6 decimal places your number is correct, and after that we not guarantee that it is correct or not. That we call the single precision, 4 byte. Double precision is the 8 byte, and in case of 8 byte you can represent the number up to 15 decimal places. 15 decimal places we can say that number is correct. So that precision, say single precision and double precision represented, we say how a float number is represented in the binary, that is given by the IEEE standard, and we are going to see that. So we call this IEEE standard 754. So IEEE 754 representation. So there are many standard, and this standard is required because whenever many programming languages or many you are checking the things on some web page or many type of device, portable programs, we have to follow the same standard. So that is a standard to represent the binary number into this. I am going to clearly show you that how we are going to represent the number in 32 bit, that is 4 bytes. So I can write here 1, 2, 3, 4, 5, 6, 7, 8. 8 bits. Then I am saying writing next 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. And next 8 bit 1, 2, 3, 4, 5, 6, 7, 8. Next 8 bit 1, 2, 3, 4, 5, 6, 7, 8. So we will see in this video that if I am writing the number 16.7556 in this representation. So first 8 byte, next 8 byte, next 8 byte. What are the these bits? Next 8 bits. What are the these bits? Okay. So the very first thing you have to check that whenever a number is represented, so this number is changed into the binary, that is something 0, 1, some pattern is there, first 8 byte and next 8 byte. So this number is actually this number is actually convert into the represent into the 3 parts. That 3 parts you have to clearly understand. I am going to show you that what are the 3 parts. So I write something like this value, but I will not take exactly this value. So I convert that because these are the 32 bit, 1, 2, 3, 4, 5, 6, 7, 8. Then okay, this is a space 8. Next 8 bit 16, next 8 bit 24, and next 8 bit total 32 bits. Out of these 32 bits, the 3 parts are there. 3 parts means that first part represent the sign. So this first digit represent the sign. After that, next 8 bit digit 1, 2, 3, 4, 5, 6, 7 and 8. Next 8 bit represent exponent, and after that actually here I can say that like here we have the 1 byte plus plus here we have the 1 byte plus here we have the 8 bit 1 bit, oh sorry, it is a 1 bit plus 8 bit plus here I'm writing plus. You have to I write that you have to understand that what are the remaining bits. The remaining are the 23. I think 23 plus 1 24, so total 32 bits. Out of that 32 bits, first bit is to represent the sign. So if you take the positive number or negative number, then this bit becomes 0. This bit for positive number this bit is 0, and for negative number this bit is 1. After that, next 8 bit represent the exponent. Actually this number is converted into the exponent form, that is 1.6 into 10 to the power something. So that 10 to the power something value is represented in the 8 bits, and after that in these 23 bits, menti size represented. So in this program, actually in the last video I also show you that how we can check that. So I am taking this value, that is 16.7556. So I am running this program. Okay, I will run that program later, but first we calculate that what are the bits. So if I run this program, that I take the float value 16.7. So I am representing here with the help of this printf function. I am printing here that what is the bit pattern for this number. I will explain this code also, but first I am going to show you that how this number is going to be changed in these bits. Okay, so for that I also use the calculator. Let me open the calculator. I also use the calculator, binary calculator, so that I can convert some numbers into the binary. And then we also use this website, that is repeatables.com. So you can see here I use this website to convert some number into the binary. So for writing here decimal, I can check that what is the number of that binary. So these things I will check also. Here I am going to show you that how we are going to represent this value into the binary. Then with the help of this program, we are going to check that our number is actually correct or not. So here we are. Actually first you have to convert 16 into the binary, then you have to convert 7556 into the binary. So I can use the calculator. I am using this calculator. In this calculator I am converting the 16 into the binary. So I write here 16. Okay, in decimal it is 16, but in binary it is actually in 8 bits it is 0001 and 4 zeros are there, but because we take these 4 values, so I am taking 1, and after that 4 zeros are there. So actually your number is so from here I am writing this number 1, after that 1 2 3 4 zeros are there. So it is 1 2 3 4 zeros and 1. So this number is actually 16. Dot I am writing here. Point, actually now you have to convert this number. So if you know the method that how convert point decimal numbers, so you have to multiply by 2, and either it comes 1 point something or 0 point something, you have to take that value. So there is a different process, but that's this website. I am writing this number 0.7556. So I directly go to the website 0.7556. That is a very simple method. We can also discuss that in some video, but here I am saying that if you write 0.7556 into the binary, so I am taking this number. So this is also matter that how many bits you are taking, but actually we have to make that total 32 bits. So we are going to see that how we are going to represent that, how many bits we are taking. Okay, so this is the value, but after that, after you convert that, after this value is converted into the binary like this, it is converted into the binary, so its value is actually 16.7556. So what is the next thing we do? We have to normalize this number. The normalize means actually you have to 1 before this only, after that decimal, and then other values you have to write these values. So I am taking these values, and here I am printing that values. So this decimal is not here, actually I normalize that. And you know that this value is actually into multiplication sign is here, 2 to the power actually you move the decimal in this direction. So 1 2 3 4, 2 to the power 4. I think you got this. So actually in normal form your value is this. I convert that into the binary. I convert the 16 into the binary. I convert the 75556 into the binary, and finally I normalize that. So I am moving this decimal point here and here. So when I put here, so I move it 4 place, 1 2 3 4. So 2 to the power 4 numbers. Okay. So what we are going to store, that is the very important things, that we are going to store this number. Actually this is the mantissa, and this number is exactly stored here, exactly same in these 23 bits. Actually out of that 32 bits, in last 23 bits this number is going to represent as it is, and exponent is the value is 4. So 4 we are going to represent here in these 8 bits, and this bit remains 0. So what I am writing, I can write that first bit is 0, that is the sign bit. After that we have to write the exponent. So here I am to write the 4 number. 4 is going to store in 8 bits. So 1 2 3 4 5 6 7 8. 4. How you write the 4? You have to convert the 4. But here the point here is, because here we know your value, that means your this exponent value, that is 4 in this case. We are not going to store this one. We are not going to store this decimal value. We are not going to store 2 to the power nothing. What we store? We will store only this part. Actually this part is enough here, because computer already know 1 is before that, and we store only 4. So I am saying again that we store only 2 parts. One is this part is the mantissa. We not store the 1, we not store the decimal point, we store only this value after decimal point in these 23 bits, and we store the 4. So now next point is, this 4 is actually not going to store like this, because we have to store positive numbers here and negative numbers here. Maybe some value is 2 to the power 34, something like that. So I am going to show you that. So some number is 2 to the power minus 4, 2 to the power minus 10, so minus negative value. So we not give the sign here positive or negative, but what we will do, we will add 127 in the number. So if this is some negative value is there, suppose you are this is that 2 to the power minus 10, then you have to add 127, that we call the bias, and this is used because there is no positive and negative, we not write. For now our calculation I am taking this 4, so this is 4 in our example. So I am adding 4 in this. So actually I am doing this 4 plus 127, and what is this value? I can use the calculator. 4 plus 127. Okay, here decimal I am taking 4 plus 127. It is happens always 127 is added as a bias. So 127 is added in this, it becomes 4 plus 127, and this value is actually becomes 4 plus 127. Okay, sorry, 4 plus 127 is equal to 131. So this value is actually 131. Now represent this 131 into the binary. This value is actually converted into the binary. So I am using this 131 in binary. Yeah, this is the value. So 131 is actually 130. It is written in 4 places. 1300011. 1300011. So that is the number, that is 131 is represented. So in these next bit, this value is printed as it is. So I am taking this value, Control V, Control C and Control V. So this is the positive part number, this is the exponent. Actually whatever the value of 2 to the power comes here after normalization, you have to add 127 in that, and whatever the value comes, convert that into the binary, and that is your exponent value. And after that, what is the mantissa? The mantissa value we have to take here. So here is this value, I am taking this one and put that as it is. So actually how many bits are there? It is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 okay, I can write 20 21 22 23. Yeah, we have to do the more calculation according to that, like 0.7556. I think if finally it comes 1, then we can add the 30. But if they note, actually I am believing on this website, and this website is saying that 0.7756 is actually this number. If you follow that process and you proceed this process, then you can find these digits are also clearly. So if I put all that bits together, that is our answer, that I am going to check in our compiler that this value is actually value or not. So this value is IEEE 754 representation of a number, and when I remove all the space, so these are the 32 bits. So your number means 16.7556. that number, when you represent in the 32 bits, is represented in this 0 is tell you that number is positive. The next 8 bits represent to you that whatever the value of 2 to the power 127 is added in that, so that, and after that next 23 bits tell you the mantissa. So I write here to represent you, but this is not the correct answer. This is the correct answer. I am going to check this. So I already write that in the program. Float x is equal to 16.7556. I execute this. If I run this, I am going to take the answer. I am going to explain some things in this course also, sorry, in this program also, but first we are going to see that our answer is correct or not. So in this I am taking this value, Control C, and I am representing here that this number is the actual number and our value is this one. So you can check that whatever the number we give, we can identify that how a number is represented into the binary. So 16.74, according to my calculation, it is represented in the binary like this. Out of this, first bit is the positive or negative, second bit is the exponent, and third bit is the mantissa. So you can see here that I think we are correct. We are correctly representing this number. Okay, so I am also using the calculator and this one. Now I am going to explain you this code, that how I write this code. This is written in C programming language, but some other concept is also required. So what I have done here, that suppose I take either character variable or float variable or anything. So we take a value float. After that I am creating a pointer p, and p is equal to address of x. So this x is there. Address of x is stored in the p. I take the void type pointer because that can store different any type of address. After that I create integer y, and actually we are converting this value, whatever the bits are stored at this address p. C is very good language. You cannot do these type of things in the Python, but in C we have better control on the memory, so I can exactly see that what are the memory pattern. So I convert that number into the integer, and then I do the AND operation with 1. So if you want to know about this code, I can explain about this also. It is very easy. Just try to understand that what I have done here. I have done here that this is the this is the right shift operation. So suppose there is some pattern inside y, that value is stored in the form of numbers, some pattern is there. So what I'm going to do, I am doing the AND operation. I am going to do the AND operation of, suppose there is the number, I am taking this number only, not a problem. You can understand the point here. Suppose I take this number, this is our actual number. After that I am writing here 1. So represent 1 is represent like this, 0 0 0 0 1. This is 1. You see, this is the 1. This y is the actual value. This is the value, and we do the AND operation on these two. So the last bit, if last bit is 0, then it remains the 0, and other bits becomes 0. So when you find the value, this value comes either 0 or 1, because all these values. After that we shift this number in the right direction. So because of this operator, first value is changing. First it is shifted by 0, then it is shifted by 1, then 2, 3, 4, 5. So when it shifts by 0, this thing is actually removed and 1 0 is added. So now next digits comes here. So next digit also take the AND operation with this. Now we will get 1. I store that into the array. Again I shift that. So in this way I am identifying. What are the bit pattern. So 0 is added, this 0 is removed. So what is the bit pattern? With the help of this operation, I store that into the array, and finally I am printing this value. So you can check, but our main point is that how the numbers are actually represented in the memory. So these are the numbers. So two video you have to see. That one is the previous video in which I already shown that how negative numbers are represented in the two component, and here I am showing that how decimal numbers are represented in the IEEE 754 standard. These things are very important, very confusing things to the student. But if we know the exact pattern, that how this value are representing in the memory, then it is very that means beneficial to us. Okay, so if you see that we will explain about the also that let's say left shift operator, right shift operator. So when you know exactly how floating points are represent, how integer represent, then we exactly know that how these values are representing in the memory. Okay, so that's it for today lecture. I will see you in the coming lectures if I show some.